Good evening. Welcome to another evening, or perhaps the first evening of these videos. Tonight I'm walking through my neighborhood and I started looking at these lights, and the experience of the camera is not quite the experience of an eye looking at this light. So I'm gonna have to do a little bit of explaining. But what I want you to imagine, and if you can, go into a dark room and turn your flashlight on your phone and turn it to your eye and take a look at that light in the dark room. What you'll see is you'll see a small rainbow, a very defined rainbow, perhaps this far away from the light. And then you'll see a lesser defined rainbow about this far from the light. And so one question is, why are there two rainbows? Another question is, why is there a rainbow at all? Why don't I just see the light as it is? Why do I see a light and a rainbow or multiple rainbows around it? So let's start here. When light goes through your eye, what are you really seeing? What does it really mean to see a light? What is light really made of? And how does light get from that lamp into your eye? What is really traveling through space, through the air, and getting into your eye? Well, hopefully you said photons, right? Light is made up of little particles that are flying in all directions and eventually arrive to your eye. And your eye gets smacked by a photon and turns that energy into electricity, or not electricity, but chemical energy, and that travels to your brain, and voila, you see light. But you can also think of light as a wavelength and a wave. And light behaves both as a particle that streams through the air and hits your eye, but it also behaves like a wave. And what I mean by that is your eye is a little hole, right? Your iris can open and close. And so truly your eye is like a little camera with a little hole at the end of it, or at the opening. And what happens is when light goes through that, it behaves like a wave. So this is going to take a little bit of explaining. Let's go to the ocean. If a wave were traveling through the water and it arrived at two walls, a wall that was, for example, let me show you on the ground here. Here we go. So if light were traveling or if a wave of water was traveling across the ocean and then hit the wall, this right here is all land, and this is a wall right here, and then it comes to land, and then you have another wall right here. So if light were traveling and boom, hits the wall, the part of the wave that is right here is going to be able to travel in, right? So that's basically, or what happens when the wave hits here. All of the individual points of the wave within this space are essentially what's the word, like continuing in all directions, essentially, is how you can imagine it. This isn't necessarily an explanation, but it's more of a description of how the behavior of a wave can be, or how the behavior of a wave is. It's not a description of why. That's another video, and I don't actually know why in this moment, but all of the infinite points that are within the space between the two walls, and therefore are the infinite points of the wave that travel past the hole in the wall, aka the slit or the hole or the aperture or the hole in your eye, they're all radiating in different directions, and if they just kept going straight ahead, they would all be in the same phase as one another. For example, if you have one wave that comes through, all particles in that wave go straight and they all build and they collect together. And then if you have another wave that comes through, all particles in that wave are part of the same phase and work to just have one wave. But if you have one wave that is kind of going this way and then another wave that goes this way, when those two waves hit, different parts of the wave are going to interact and cancel part of each other out. And so you're going to get little holes in the waves. And so that's what you see when light goes through an aperture or a hole. You get straight ahead, you have the wave goes strong, and then there's a general region of space where the wave is canceled out and you don't get it. And then there's a region of space where where the different phases have collected and strengthen one another again. And so you get like a little line. And then you'll get another region of nothing, and then another region of strength and wave. So when you take a look at the light here, when you see the first rainbow about this far away from the light, and really it's a lot closer, it's more like this close to the light, my finger, like this. But if it were this far away, that's the first area of strengthened wave. And then the rainbow that's a little further out, that's the second region of strengthened wave. And the region in between where there's no rainbow, that's the part that it got canceled out. So what happens is light enters your eye. It enters your eye, and it behaves like a wave. And behaving like a wave means that some of the light gets diffracted to the left and to the right and up and down. And so that's how you see light that's not only coming straight at you, but light that is also strengthened into a ring of light around the light. And then you see another diffraction ring that was strengthened a little further away. But then you ask yourself, why would that ring be a rainbow? Why wouldn't it just be a ring of white light? And that's such a good question. Good job. I would ask you in return, well, What's the difference between red, orange, yellow, green, blue, purple? What's the difference between them? Because that difference is going to define the reason why they travel different distances in your eye when they diffract, and therefore are seen at different distances away from the light as appears in your eye. So what's the difference between red and blue, for example, or any other color? Well, the difference is that when we think about light as a wave, one way to think about a wave is think of the ocean. You have waves that are really tall. You also have some waves that are a little shorter. And they rise and fall. And they rise and they fall. And they have a crest and they have a trough. The top is the crest and the bottom is the trough. And any wave that comes through, so if this is a flat ocean and all of a sudden you get a wave that starts and then goes down, as soon as it comes back to normal, you just experienced a full wave. And the distance from the beginning, middle, all the way to the end, the difference from the beginning to the end is the wavelength. So, what do you think is the difference in wavelength between red light and blue light and green light and yellow light and all other lights? The wavelength difference is modeled in nanometers. So light is has a wavelength that is so freaking small. It's just little teeny waves that are getting traveling through space. It's really amazing. They're just freaking nanometers in length, which is like a millionth of a meter or more. I think it's a millionth. It's 10 to the negative 9 for the folks out there who care. So some red light, for example, I'm just going to throw out some random numbers, might be, I think this might be right, 10 to the negative, oh man, I can't remember. I think maybe some wavelength is like 10 to the negative 4. I have no idea. And we're talking about visible light here, but some lights, like red light, is a particular wavelength, and let me think. Red, orange, yellow, green, blue, purple. Which one has more energy? Blue light has more energy, which means the wavelength is shorter. Blue light shorter. Red light's longer. I think that's correct. So anyway, the thing is, you can think of a wavelength as, if we go back to the idea of a wave hitting two doors or two walls, and a bit of the wave goes through and passes through. What you can think of is, depending on the size of the slit, if it's a very small slit, then the wave particles, or the points on this side versus this side, again, this side versus this side, they're going to be very close to each other, right? So they're not going to really have much opportunities as they promulgate further out. They're not going to have many opportunities to cancel each other out. So you're just going to basically see like one light. But, and maybe like a blurry light everywhere. But as the light gets bigger, as the hole gets bigger, the distance between over here and over here is much greater. And so this light has a much greater opportunity to cancel out eventually the light that's up here. when they eventually meet over here or down here. And so what's gonna happen is as the aperture gets larger, or the hole gets larger, you're gonna see differences. Yeah, you're gonna see differences in the distance. That you're gonna see differences in how far the light gets to diffract. Maybe it diffracts this far, maybe it diffracts this far. It depends on the slit. So like as your eye, I think, contracts and expands, it's gonna change how far or in what way the light diffracts. But what I'm trying to get at is that the difference between red light and blue light, for example, is wavelength. One is much longer than the other. So effectively, you can think of the slit. It's the same thing as thinking of the slit as bigger or smaller. If you make the wavelength bigger or smaller, it's going to change how far the light diffracts and in what way and in what pattern. So yeah, exactly. So as the wavelength gets larger or smaller between the different lights, they diffract at different distances, and so you're gonna get a rainbow effect around the light because some wavelengths will diffract this far, some wavelengths will diffract this far. And in my case, red light diffracts this far and the green light diffracts this far. So the red light is the one that diffracts the furthest away. And let me think if that would make sense to me. Red light should diffract the furthest. Well, we said red light has the longest wavelength. Red light has the longest wavelength. I'm not sure if I have an explanation for this, but if red light has the longest wavelength, I guess you can think of... Oh, I guess it's counterintuitive to me. I would think red light would diffract the least, because given its long wavelength, as it goes through the slit, it's going to have less opportunities to be out of phase. If it has less opportunities to be out of phase, I think you're going to see the greatest straight to like relatively straight boundary of strength and light. Man, I don't know. So you're gonna see a lot of red light all the way around. Oh, that's why. Oh, no way. Oh, that's so cool. Okay, so here's the thing. If you see a diagram of the light that goes through an aperture, yes, that's so freaking cool. Oh my gosh. Okay. As the light goes through the hole, there's gonna be the greatest thing you'll see on is light that goes straight forward. And then the next thing you'll see is like one or two strengthened patterns, right? But the greatest thing you'll see is just a general area of brightness. And that's the case for any color. And so what I'm realizing is that what I do truly see around the point source of light is I see a general halo of white light, and then I see maybe like a greenish or yellowish sort of color, and then I see red very significantly. So I'm not really seeing a true rainbow. I don't see blue, at least not in the first one, not in the first rainbow so clearly. So what I think is happening is all colors, red, blue, green, they're all combined. They all have a general region that they diffract into, and all of them are combining into white light. And so you see a general white halo. But then which one diffracts, which one is able to maintain its strength the furthest? Well, it's the one we just talked about, red, that has the longest wavelength, because it gets to stay in phase the most. It doesn't get canceled out as well as does something like a small blue, because the small blue is oscillating so fast that it can cancel out its other blue wavelengths after a very short distance. So blue gets canceled out pretty quickly as you go away from straight on, but red doesn't get canceled out as easily as you move away from straight ahead, which means red goes the furthest. And so red is the last color on the boundary because it's the one that made it the furthest sideways. And so in the middle space, you're just gonna see a bunch of colors mixed, and that'll turn into white-ish light. And then on the very end, you don't have any mixing because the only color left is red. Wow, that's so cool. Wow. What a neat thing. All right, y'all, thanks for sticking through it with me. Thanks for enjoying this adventure. Now I'm just gonna be staring at these lights. It's probably not so good for my eyes, but I'm just so curious. It's such an interesting phenomenon. And now I'm curious if I see any blue at all, or if no, I don't think I do. I feel like I do, but I feel like I'd probably just be lying to myself. It's really much more like greenish and red. Wow. So cool. All right, y'all, thanks for experimenting, and thanks for going on this walk with me. Appreciate it. Have a good night. See you later.